We're going to shift gears in our new unit to start talking about motion. Again, motion like we have in Unit 1 and in Unit 2, but motion this time that is not in a straight line. Everything we've done up until this point has involved motion in a straight line. Now, sometimes it was two dimensions. Sometimes something was pulled to the right and something was pulled upwards, and then it ended up going in between, but it was still a straight line. Today we're going to start talking about circular motion, objects moving in a circle, specifically uniform circular motion. Uniform circular motion, or sometimes we call it UCM, is circular motion, and I think that's pretty self-evident what that means. It's circular motion, an object moving in a circle with a constant speed. There are situations where an object is going in a circle and not traveling at a constant speed. There are lots of them. Many of them can be approximated by treating it as uniform circular motion, but strictly speaking, they aren't uniform circular motion. But there are also lots of other situations that are truly uniform circular motion, where an object is going in a circle and is going at a constant speed. There are three terms that we will identify or define in order to set the foundation for uniform circular motion, in order to set the foundation for these objects moving in a circle at a constant speed. Those terms are frequency, period, and speed. Frequency we're going to define as the number of revolutions that take place per second. So we go back to the cat on the ceiling fan video for a second. Okay, we could have counted the number of revolutions that the cat was making, all the while timing it with our watches, seeing how many revolutions it makes per second. That would be the frequency of revolution. Okay, the number of revolutions per unit time, generally per second, but it could be per hour or per minute as well. The number of revolutions per unit time. Now the symbol for frequency is a small f. Make sure you don't get that mixed up with force. Force is a big F. Okay, we need to make this small so that we don't mix it up with force. Frequency is the number of revolutions over the time. Now, the units for frequency, if we take a look at the equation here, the units for frequency would be revolutions per second. But another unit that we can replace that with, that means exactly the same thing as a revolution per second, you guys have heard this before, you just maybe didn't know what it meant. It's a hertz. When you turn on the radio, what radio station do you guys listen to now? 105.1? Okay, so Nick listens to 105.1. I don't even know what radio station that is. But that's an FM radio station, and that says, if you look at the dial or you look at your radio, it'll say 105.1 megahertz, MHZ. That means that wave that carries that sound, that wave that carries that radio broadcast, has 105.1 million cycles per second. 105.1 million hertz, or 105.1 million cycles per second. A hertz is one revolution or one cycle per second. Hey, that's the standard unit for frequency is hertz. But sometimes it's convenient to put it into megahertz or kilohertz when you're talking about a radio or whatever. Okay, this is the standard unit that we'll use though. Frequency, the number of revolutions over the amount of time that takes place. Period, on the other hand, is the time per revolution. How much time it takes for one revolution. So again, if we think about the cat on the ceiling fan video, the frequency is how many revolutions the cat made in 1 second. The period would be how long did it take for one of those revolutions. Does that make sense, the difference there? How many revolutions in 1 second versus how long did it take to make one revolution. The equation that describes the period is going to be big T. T is time. Little t is just any time, and time in general. Okay, it can represent the time for a revolution. It can represent the time that it takes me to walk across the room. It can mean the time that it takes us next Tuesday to drive in the bus to West Edmonton Mall. Okay, little t is any time. Big T specifically is always the time for one cycle or the time for one revolution, the period. We're going to find that period by dividing the time, the total time, by the number of revolutions. So in other words, it's the exact inverse of the frequency. If frequency is number of revolutions per time, then period is time per number of revolutions. The units for this would be seconds per revolution, or what we often do is just say seconds. What's the period of this? 3 seconds. What's the period of the Earth's revolution around the sun? 365 days. Okay, 364 and a quarter days. Speed, we already know what speed means, right? Speed is how quickly something's traveling. We talk about the speed of an object in uniform circular motion. We're talking about how fast something's moving at a constant speed around that circle. We know the equation for speed. V is equal to d over t. Pay really close attention to what I'm about to do here. The distance around the circle once is defined as its circumference. The equation for circumference is 2 pi r. So we're going to say the distance around the circle, delta d, is 2 pi r, the circumference. If we're using the distance around the circle, then we also need the time around the circle. The distance around the circle once is the circumference. The time around the circle once is the period. Yeah. So the equation for speed that is specific to uniform circular motion, right? D over t always applies. But the one that's specific to uniform circular motion would be V is equal to 2 pi r over t. In other words, the circumference over the period. Now, there's a couple of these equations, one of these equations that appear on your data sheet. This appears on your data sheet. V is equal to delta d over delta t. V is equal to 2 pi r over t also appears on your data sheet. This one does not appear on your data sheet because this one is more of a definition. You have to remember what frequency is, and if you do, then you're going to be able to get that equation. This one also doesn't appear on our data sheet. But this one does. T is equal to 1 over f. Look, if frequency is revolutions per time, and period is time per revolution, then you know they're the exact inverse of one another. That means T is not equal to f. T is equal to the inverse of f. And similarly, f is equal to the inverse of t. So we've seen 4 equations here today. This one, this one, this one, and this one. 2 of them do appear in your data sheet. 2 of them are really just definitions. Let's take a look at problem 5.1 on page 250. This is chapter 5, by the way, for those of you who haven't downloaded the entire textbook, chapter 5. This is the hard drive in figure 5.16. It doesn't matter about the picture. Okay, it stores down on a thin magnetic platter that spins at a high speed. The platter makes one complete revolution of 0.00833 seconds. Determine its frequency in hertz and in RPM. What does RPM stand for? Revolutions per minute. It's a valid unit for frequency, just the same as kilometers per hour or miles per hour is a valid unit for speed. It's just not standard. Standard for speed is meters per second. Standard for frequency is hertz. We have to be able to get from hertz to revolutions per minute. And we'll show you how to do that in just a moment here, okay? So we get this hard drive that's spinning around. It's making one revolution in 0.00833 seconds. Can you tell me, please, what that number represents? We defined 3 terms earlier here: frequency, period, and speed. Can you tell me what that number is? Is it frequency, is it period, or is it speed? Which one is it? Which one is it, Hayden? It's the period. right? The time for one revolution, big T. Don't call it little t, because it's not just time. It's not just, it is a time, but it's not just any time. It's specifically the time for one revolution. It's the period. So T is equal to 0.00833 seconds. We're looking for the frequency, looking for F. Now we know that frequency is, if you look back to those equations again for a moment, it's the number of revolutions per time. That's not helpful in this particular question. But we also know that period is equal to 1 over F. We can rearrange this to solve for frequency. Take the F up, take the T down, and then get 1 over T. So frequency is number of revolutions per unit time, but it's also 1 over F, or 1 over T, I should say. 1 over 0.00833 seconds. What do we get when we do that? 120.048. Thank you. 120.048019. What would the units for that be? Listen, we just use standard units when we're calculating this, right? Period is in seconds, so we're going to get standard units in our answer. The standard units for frequency are, Rucker? Hertz, right? Now, we wanted to find the frequency in hertz, so this is a final answer, so let's round it to the correct number of digits. It's 120. But now we have to figure out what it is in revolutions per minute. How many seconds in a minute? 60. So I'm either going to multiply this number by 60, or I'm going to divide this number by 60. If you're anything like me, you have trouble thinking about, am I going to multiply or divide? You always have trouble with that. I always do. Still, to this day, I have trouble. Do I multiply or divide? You know what I do a lot of times when I come to situations like this where I'm not sure whether I multiply or divide? I guess. Seriously, I guess sometimes. And that's okay. It's okay to guess as long as you check your guess. Okay, let's say I divide by 60. I'm guessing divide by 60 here. Let's say 120.04819 hertz divided by 60. That's going to give me about 2 revolutions per minute. Does that make sense? If it makes 120 revolutions in 1 second, is it going to make 2 revolutions in a minute? Oh, it's going to make more, isn't it? So it couldn't have been divided by 60. It must have been multiplied by 60. So I guess wrong. Big deal. It's got to be the other one. It's okay to guess if you have to, as long as you check that guess to make sure that it makes sense. We'll multiply that by 60, and I think we end up getting 7.20 times 10 to the 3 RPMs. 7.20 times 10 to the 3 revolutions every minute. It's pretty standard, actually, for a computer hard drive. You can get hard drives that spin faster. What would be the benefit of giving a hard drive that spins faster? Yeah. Yeah, quicker access, right? Quicker access to it. You're trying to get data. If this thing is spinning at 7,200 revolutions per minute, you're going to be able to access the data on various parts of the hard drive fairly quickly. But if it's spinning, say, 10 or 20% faster, then you're going to be able to access all the information that's on there 10 or 20% faster, right? So the faster it spins, the quicker access you have to it. Yep.
Also, more chance of traveling as
Uh,
well.
well, I mean, the faster something's going to spin. I mean, these are pretty. These things. A computer hard drive is a pretty sensitive piece of equipment to begin with. You talk about dropping it. I mean, this hard drive is spinning at 7,200 revolutions per minute. You can imagine there's a little reader basically that gets really close to this spinning hard drive. You can imagine if something's out of alignment, just the slightest little bit, the damage that's going to be caused when this thing is spinning at 7,200 revolutions per minute. So yeah, Rutger, you're right. If it's spinning faster, it's even more of a problem. But it's pretty sensitive to begin with. You don't want to take a hard drive and drop it on the floor. Otherwise, it's probably not going to work anyways, even at 7,200, Rutger. Okay, let's take a look in your notebooks, please, at these 3 questions on page 250. We'll give you maybe about 4 or 5 minutes to see if you can do these, and then we'll take a look at them as a class. All right. If we have no issues with these three questions, if you've got them all, then let's take a look at one more example on page 251, 5.2. This one says a pebble is stuck in the treads of a tire at a distance of 36 centimeters from the axle. There's a picture there that I didn't include there, but here's your tire. Okay, there's a pebble that's stuck in the treads of that tire, and it's 36 centimeters from the axle, or 36 centimeters away from the circle. It takes 4 seconds, or 0.04 seconds, for the wheel to make one revolution. What's the speed of the pebble at any instant? We know that the radius here is 36 centimeters, or 0.36 meters. We know we have to convert to meters, so let's write that down now. We know that something is 0.40 seconds. Can you tell me what that is? It's not speed, is it? Yeah, it's the period. It's the time for one revolution. It's big T, the period. We're looking for the speed here. Now, we know the speed can be given by the equation V is equal to delta D over delta T, but that distance is not the radius, because the stone hasn't traveled the radius of the circle. It's traveled the circumference. So we're not going to use D over T. We're going to use 2 pi r over big T. It becomes 2 times pi times the radius of 0.360 meters, divided by 0.40 seconds. When we do that, we end up getting 5.7. 2 digits, it would be 5.7. Okay. 5.7 meters per second. I used to have this little bike computer on my bike. It was on the handlebars of my bike. It's just literally about the size of your watch. And it would give me the speed of my bike, it would tell me the distance traveled, and so on and so on and so on. I'm a numbers person. When I go running, I have to have the heart rate monitor on. I have to have the GPS so I know how far I've ran and how fast I've ran. And to me, that motivates me. Okay? When I'm biking, I like to have the same kind of thing. I like to know how fast I'm going, how far I've gone, and so on and so on and so on. I don't have this bike computer anymore because now I just use a GPS. It's a lot simpler than the old system. But the system that I had, and some of you guys may have had something like this too, because you can still buy these, a Canadian Tire or a bike store or whatever. It uses a little magnet that you attach to a spoke of your tire, of your wheel. Okay, now that little magnet, as you pedal, okay, that little magnet turns around. Okay, so there's a little magnet in here somewhere. Maybe it's near the edge of your wheel. Okay, it doesn't really matter where it is. Okay, as long as we know that distance. The computer knows that distance. You program in that distance into your little bike computer, 36 centimeters or whatever it happens to be. The radius of revolution of this little magnet. As this magnet spins around, it goes past this other little detector that's on the fork of your bike. So every time it goes around, your bike knows when it's made one revolution, right? Your bike knows what the period is, because the computer has timed how long it took for this little magnet to make one revolution. That's the problem we have here, right? The computer just figures it out for you. Okay, you physically measure and program into the computer that radius. Your bike will measure the time of one revolution for you, and then the computer will calculate the speed based on 2 pi r over t. Does that make sense? It'll also measure the distance and tell you how far you've traveled by just going 2 pi times r. And it keeps adding those revolutions up as you make more and more revolutions. Parker, question?
I have one of those on my bike, but I put the magnet really close to the inside of the wheel, and I just broke up the wheel of that wheel base.
Yeah. Well, what happens with that is no, not at all. You don't put it on the outside of the wheel, and you are supposed to program the wheel radius, but because of the way that the spokes are set up, Rucker, the spokes are set up like this. The way that this thing works is that you put it down here, and then you kind of slide it up as far as it'll go. When it stops, okay, that's where you leave it, right, where it stops there. So basically, as it spins around, it wants to go to the outside, but it can only go to a certain point this far. Now, you program in the radius of the wheel, but the computer knows that that's not the real radius. The computer essentially knows to subtract that distance away from it. So if you put it where you're supposed to, the speed is actually relatively accurate. Okay, if you put it in the wrong place, then all bets are off. You're going to end up with a speed that's not very close to being accurate at all. Okay, and if you make the radius half of what it's supposed to be, well, then you're going to make your speed off by a factor of 2 then, right? So you think you're going 50, and you're really going 25.
Yeah, I would like to jump.
Rucker, you're absolutely right about that. You're absolutely right. It doesn't matter where you put this, as long as you have the detector that will match up with that. What matters is the point on the outside of the wheel, because that's what's moving on the ground. So you're absolutely right. It doesn't matter where you put that. It doesn't matter where you put that, as long as the outside of your wheel, that point on the outside of your wheel, has that certain radius of 36 centimeters or whatever it is. Yeah, you're right. Yeah, good point. Okay, let's take a look at, having seen another one, let's take a look at 2 more questions, page 251. These are going to be a little bit more challenging than the last 3 that you did, but they still should go fairly quickly for us. Let's take a look, please, at question number 2. Number 2 says, in 2006, an Alberta astronomer discovered the fastest spinning collapsed star called the pulsar ever found. It has a radius of only 16.1 kilometers and is spinning at a rate of 716 hertz. 716 cycles per second, or revolutions per second. That's a pretty fast spinning thing, right? That's like saying the Earth spinning around 716 times per second. We spin around once in 24 hours. This thing spins around 716 times in 1 second. So that's something that you probably don't want to be standing on. You're probably going to be flung off the surface of that if you're spinning around at 716 times per second. We want to know what the speed of it is at the equator. All right. Let's say that the radius is 16.1 kilometers, which is 16,100 meters. We got to be in meters, right? We got to be in standard units. We know that the frequency is 716 hertz, 716 revolutions per second. We want to find its speed. And we know that V is equal to 2 pi r over T, and that equation is on our data sheet. We know what R is, easy enough. It's 2 times pi times 16,100. Divided by the period. The period we don't know. We got to find it. But the period we can find by using the frequency. It's going to be 1 over 716 hertz. Somebody have a value for that, please? Lane? 001396. And that's going to be in seconds, right? Since our frequency is measured in hertz. Let's take that number, plug it in down here, 0.001396 seconds, and we get a speed of 7.24 times 10 to the 7 meters per second. So this thing at its equator is traveling really, really, really fast. Now, we haven't yet had any questions involving, say, loops on roller coasters or swings that go in circles, swing of the century rides. We haven't had any questions on that. A week from yesterday is when we're going to put a lot of this into play as well. I told you guys last week, conservation of energy was one of the biggest things that we do on our field trip. This is pretty big too, because there's a lot of stuff in amusement parks that involves circles, uniform circular motion. Let's talk about what happens now to the object as it goes around the circle. As the object goes around a circle, it wants to go in a straight line. Inertia wants to take this thing in a straight line. We define inertia as a tendency of an object to keep doing what it's doing, a tendency to resist a change in motion. Okay, if I'm going in a straight line, I want to stay going in a straight line. If I'm not going in a straight line, I want to go in a straight line. The only thing that's keeping me from going in a straight line is a force, a net force acting on the object. There is a net force acting on an object going in a circle. We call it a centripetal force. We'll talk more about that centripetal force tomorrow. That centripetal force keeps it from going in a straight line. But if we remove that centripetal force, then the object will go in a straight line. Okay, back in the 80s, the Mindbender roller coaster that you're going to ride next Tuesday had an accident. There was I think 2 or 3 people that were killed and several people that were injured. That happened when the roller coaster train went around a turn. That roller coaster normally has a centripetal force that keeps it from going in a straight line. But on that day, something happened that centripetal force wasn't there. So what happened to the cart? It went in a straight line. If there's no centripetal force, no unbalanced force to keep it from going in a straight line, it will go in a straight line. So in other words, if let's say I swing the keys, my keys around my head like this, there's a centripetal force keeping these keys from going in a straight line. It's provided by the string and ultimately my hand. It's keeping it from going in a straight line. If I let go of these keys, the centripetal force is gone. What happens to these keys? They go off in a straight line. But they don't go off in a straight line like this. They don't go out from the center. Rather, they're going to go off in a straight line like this. Okay, at this point, they would go off in a straight line like this. In other words, the velocity of this object is always a tangent to the circle. It's always a line that's drawn kind of flat along that circle. Yep? No, that's a good question, but we'll talk about that tomorrow as well. There's two forces that you hear about. One is centripetal force, and one is centrifugal force. Centripetal force is a force. It's a real force. It's legitimate. It exists. Centrifugal force, which you also often hear of, that's the force that pushes you out. That's not really a force. And we'll talk about how you go out if there's not really a force that pushes you out. Again, we'll talk about that tomorrow. Okay, Roger? Yeah, we'll talk about it tomorrow, though. Yeah. I'm going to show you another video here right now. This one is a Cirque du Soleil video, which is the best one that I could find that shows you the motion of an object when that centripetal force is removed. Okay?